all you Gretas and Shatezcats out there. Welcome to APES Unit 3, Section 3, Population Growth and Resource Availability. So here's a nifty old-time population chart. For those of you who've done Human Geo or are doing Human Geo now, this should be a very easy unit for you because a lot of the stuff is going to be the same. So no population can grow indefinitely due to limiting factors. And one of them you could think of as light. So plants can only do so much growing. Water definitely is going to limit a population. Space, competition, predation, and disease are the big limiting factors. So those are all going to go on page 8 of your notes if you take notes in the packet. So let's move me up here. So we have what is called an intrinsic rate of increase, or R. And so these are think back to your R strategists I talked about last section of notes. They're going to grow at this exponential rate. So this is a rate of population growth with unlimited resources. So pretend you had everything you possibly could need for a population. They would grow exponentially. So that's what this looks like, intrinsic rate of increase. But in reality, hey babies. So you have I'll cover my, look at the little babies. 4 characteristics of rapidly growing populations. So one, timing of reproduction. Rats and mice can reproduce fairly early on in their life, and then they make a whole bunch of babies. So reproducing early in life. Second, bugs. Amount of time between generations is very short. So, hey, I made some babies. Oh, look, I made some more babies. So they tend to, rapidly growing populations make lots of babies fairly quickly. Length of reproductive lives. They're long and they can reproduce many, many, many times in their life. That's not a big deal for them. And last but not least, noodle bunnies. Number of offspring, or fecundity is the big fancy word you might see on a test question. But how many babies can you make? Many offspring is high fecundity, and then low fecundity would be only having a couple. So these are your characteristics of rapidly growing populations. So continuing on, we have what is called carrying capacity, or abbreviated with a K. So think back to the K strategist from the last section of notes. So this is determined by biotic potential. So this is the maximum reproductive rate of a population in ideal conditions. So there's a capacity for growth, but it's how many of whatever critter can live in an area given those resources. So think of like a fishbowl. You have a set amount of fish that could live in that fishbowl and be happy and productive, versus if I dumped like 50 fish, they wouldn't be too happy. So you have your carrying capacity of an area, how much stuff is available. So it's determined both by biotic potential and environmental resistance. So these are factors that limit the growth. So as a population reaches carrying capacity, growth rate decreases because resources become much more scarce, among other factors. So maybe food is being used up, space is being used up, available mates are being used up. So what happens to mortality, death? More things are going to die. And less babies are going to be born, because as critters see, hey, there's less space, there's less resources, I'm going to make less babies to respond to that. And that is what we call a J curve. Before we get to carrying capacity, we have a J curve. So this is your exponential growth. Real life, this cannot happen indefinitely. So this was that intrinsic growth rate. We're just growing and growing and growing, but that isn't real. What is real is our logistic growth, and that's how it's an S curve, or which stands for sigmoid. I will never ask you that. Logistic growth. So you're growing exponentially, but then as you're reaching carrying capacity, you're going to go ahead and slow down. You have more deaths and you have less births, and therefore the rate is going to slow down. So it's exponential for the first part, and then it slows down as those limiting factors take effect, whatever fact it is. So there you have. So we always start exponentially, but we will end with logistic growth because that's the one that makes sense. So usually what happens is you have this exponential growth and you have what is called an overshoot, and the population gets above carrying capacity. But then you will have what is called a dieback. So there's this oscillation of overshoot, dieback, overshoot, dieback, overshoot, dieback, as the population figures out, okay, what is like the perfect number? And populations do a good job of figuring this out on their own and stabilizing. It just takes a little bit of time. So exponential growth equation is here you go. And I'll give you what all of these things mean in just a second. But there is your equation. So we have our initial population size equals the rate of growth times a constant times or 2 the amount of time, and then the final population size. I'm not going to make you do math. This is also how you calculate compound interest, is you take that rate of growth and the constant and the time. So if you want to figure out like, okay, here's how much money I put in versus that, we will do some doubling time, but that's about it. We're not going to do too much of this math. So I'll just go through it quickly. Considering a population math has an initial population of 20, the intrinsic growth rate is 20%. R equals 0.2 or 20%, meaning each mouse produces a net increase of 0.2 mice each year. Predict the size of the mouse population 5 years from now. So if you go through and do that equation, there are all your numbers, and you would get 54.4, which would be 54 mice. I'm going to go ahead and explain doubling time to you in class, but this I'm not going to ask you to do. And then the second question is 10 years from now, and then 20 years from now. A lot of mice. So you can see how quickly it increases. Mice like to make babies. All right, density dependent factors, bottom of page 10. These are going to change their intensity depending on the density of the population. So as a population becomes more dense, these things matter more. As a population becomes less dense, they matter less. So things like competition, things like predation, diseases, parasitism, are all density dependent factors. So think even this year to last year at school. Hopefully we don't have too much predation in the hallways, but competition for things, when I have like 3 people in my classroom, they don't have to worry about is there going to be enough stuff for them. Diseases is why we're spacing ourselves out, because we want to not have diseases spread to each other. And parasitism, the more closely, elementary school, kids are all over each other. Lice is a huge, huge issue. We tend to be more spaced out in high school and not like lying on each other like the elementary schools do. But when they started doing selfies, they noticed that lice actually increased in high schools as well, because people were doing their heads together to get their pictures. So keep that in mind next time you do a selfie with somebody. Density independent factors are going to have the same intensity will have the same intensity that doesn't really depend on the density of the population. So these are natural things like floods, hurricane, fire. A flood is going to happen. It's not seeking anyone or anything out. Doesn't matter how much. The flood does not care how much of a population is there. It's just going to happen. And then things like anthropogenic or man-made, things like pollution or habitat destruction will also happen regardless of who all is there. It's just something that happens. So those are density independent factors. It can happen. One person can get flooded or a whole town can get flooded. One person can have pollution on it or a whole town. So there's a really cool video that I have already assigned to you guys through Canvas. So go ahead and watch it that way. But it's kind of a cool video with some questions that go along with it. So don't follow this link, go ahead and follow the link that is in Canvas. But it talks about the Texas mosquito mystery. So we have 4 types of, and then there's, ignore the questions in the Canvas packet, in the packet, because I have an Edpuzzle version of it for you. So then down to the bottom of page 11, we have 4 types of population fluctuations. So the first one in the picture, here we go, stable. This is going to fluctuate slightly above and below carrying capacity. So it goes up, it goes down. We have overshoot, we have dieback, but it's fairly stable. Tropical rainforests are this way. The temperatures and the rainfall stay fairly steady, so then the critters can figure out what they're doing. So that's the first kind. Second kind is erupt. So these are usually stable, but sometimes will explode and then crash. So things like algae or insects, due to seasonal changes or nutrient availability, might have a huge increase, things like an algal bloom, and then they die back. So that would be an erupt form. And then we have cyclical. These are going to have rise and fall in predictable patterns. So the blue line is the snowshoe hare and the red line is the lynx. So you have a whole bunch of snowshoe hare, but then you can see there's a decent chunk of lynx following behind them. So that's going to pull that population back down. As the lynx population goes up, you can see that snowshoe hare population comes back down. But now that the snowshoe hare population is down, the lynx population is going to crash because they have no food. If there are less lynx, then lots of snowshoe hares. That's the official noise that happens. And then you can see there's this like staggered effect of the prey goes up, then the predator goes up, the prey goes back down, the predator goes back down. So this is cyclical. We know that it's going to happen up, down, up, down, up, down. So any major predator-prey relationship will show you that. And then the last one is irregular, and there's no real occurring pattern. And so we're going between, okay, is it just chaos in the system, or if it's something that is not yet understood? So maybe there is a pattern, we just don't see it yet. So that is the next one. Then we have, this is just funny, the drama correlation law. So this is how often someone declares that they hate drama and always avoid it. And this is rate at which they create drama. And if you do not know someone who does this, you are the person that does this, just so you know. So that's just something funny. And you have survived your notes. So that is the end of section 3. Before I go, I want to let each and every one of you know that you are good enough, you are smart enough, and people do like you. And if I don't see you, good afternoon, good evening, and good God, do your homework.